Okay, last time we were talking about a bunch of different gas laws that we talked about. We saw again our Boyle's law, which is our P1 V1 equals P2 V2, uh, obviously at constant temperature. We saw Charles' law, which is V1 T1 equals V2 T2, and that is at constant pressure in that particular case. Temperature, pretty much like all gas laws, needs to be in Kelvin. We also saw Guy Lusik's law, which is P1 T1 equals P2 T2 at constant volume. We also saw Avogadro's law, which is V1 N1 equals V2 N2, and that is at constant temperature and pressure. This guy is at constant volume, that's at constant pressure, and that's at constant temperature. In addition, we saw the ideal gas law, kind of taking all those guys into account, which is PV equals nRT. This is sort of a one situation, and again, most restrictive in terms of units. So pressure has to be atmospheres, volume has to be liters, and is moles. T is Kelvin, like all other guys. And again, that's because R is 0.08206 liters atmosphere Kelvin mole. That's the gas constant, which you always have. We also saw the combined gas law, and that was our P1 V1 T1 equals P2 V2 and T2. Bad P there. And I think that was probably about all of the ones we talked about. In addition, obviously, we talked about that there's one atmosphere is 760 torr, also 760 millimeters of mercury. In addition, we also talked about STP. So STP is standard temperature and pressure. So our temperature is 273 Kelvin at that point, and our pressure is 1 atmosphere if we're at STP. And we did see a sort of conversion factor that you could use instead of, say, the ideal gas law. And that is when you are at STP, 1 mole of any gas is about 22.414 liters. So, again, that's sort of a conversion factor that you can only use if you are at STP. If you're not at STP, you definitely cannot use that. Any questions on any of those sort of gas laws? As we talked about last time, if you sort of remember this guy, you could pretty much get all these gas laws pretty much from it. So that's a good one to kind of remember. Again, what you do is it's just whatever's being held constant, you pretty much take out of it and you have that whole thing left over. Any questions on any of those sort of laws there? Okay, so where we left off was we're going to talk about some properties here of gases in terms of calculating certain properties. And the two sort of properties we're going to calculate is density and molar mass. So usually when we talk about density for gases, usually our units are going to be grams per liter in terms of the density. And if we want to calculate density, which is mass over volume, we could use this sort of shortened formula here, which is P times M. M is our molar mass. This needs to be in atmospheres. This is our molar mass in grams per mole, right? Molar mass. R is our gas constant, so that's our 0.08206. And T is our temperature in Kelvin. So if you want to calculate the density of a gas, you could basically figure out those things and plug it in. In reality, this is really based off of the ideal gas law. And you could kind of use the ideal gas law to solve this. And I'll show you that in just a second. But if we kind of just put the units in here, we do have atmospheres for our pressure. We do have grams per mole for our molar mass. We obviously have all those units for R. And then we have Kelvin. And in terms of units canceling, what we'll be left with is atmospheres cancel, moles will cancel, Kelvin will cancel, and what we're left with is basically grams on top and liters on the bottom. That gives us the typical units of grams per liter for the units when it's all said and done, which is typically the units that we do see with gases. Um, this equation here and the one on the bottom we're going to talk about really, again, kind of based off of PV equals nRT. And we'll take a look at that in just a second here. If we want to calculate something like the molar mass of a substance, so the molar mass of a substance usually has units of grams per mole when it's all said and done. You can take the density of the gas if it's given to you, or you could calculate it, and you would want to calculate it in grams per liter so that all the units pretty much cancel out. Everything else here is pretty much the same as above. R is our gas constant, T is our temperature in Kelvin, P is our pressure in atmospheres. And again, if we just sort of put in the units there, density would be grams per liter. Our R would be our liters, atmosphere, Kelvin, mole. Our T would be our Kelvin, and our pressure would be our atmospheres. Again, atmospheres here will cancel. Kelvin will cancel, and liters will cancel, again, leaving us that grams per mole in terms of the units that are left over when we do this. So why don't you give it a go here? Why don't we try one here and see what we got? So let's go with, let's say we had N2 at 27 degrees Celsius and 1.25 atmospheres. What is the density of N2 in grams per liter? And I think that's all you probably need. Nitrogen is 1401 from the periodic table. All right, so take a minute or two to see what you come up with here, solving it. Okay, so let's take a look at this one. And again, there's a couple different ways you could kind of approach it. If you remember the formula, we are looking for density, and basically density is the pressure times the molar mass divided by RT. Now, if you can't remember that formula, I'm going to show you how you could kind of again use the ideal gas law to kind of solve for it. Basically, the ideal gas law is where this equation sort of comes from. So if we look at sort of the ideal gas law, which is PV equals nRT, and we think about what's given to us, we obviously have a temperature given to us. We do have a pressure given to us. We always have R for sure. And that's about it in terms of sort of the ideal gas law. So we would want to change our temperature into Kelvin like usual. So that's going to be 27 plus 273. That's going to give us 300 Kelvin. And if I take the ideal gas law, since I do have pressure, I do have temperature, I do have R given to me. And if I solve for N divided by V, so if I solve the ideal gas law for N divided by V, that means V is going to come this way, RT is going to come the other way, and that's going to give me P over RT. Now, when we think about the units that are here, N is moles, L is volume, which is liters. That is moles per molarity, which is moles per liter, which is what I'm solving for here, which is essentially the molarity of the gas. So I can actually use the ideal gas law and solve for N over V, which again is moles per liter, which is the molarity. I then can put in my numbers here. So that would be 1.25 atmospheres. My R is 0.08206. And my temperature there is 300 Kelvin. And that is going to give me 1.25 divided by 0.08206 and 300. It's going to give me something like 0.05078. Again, the units here are going to be moles per liter, which would oddly be the molarity of the gas if I was interested in the molarity of the gas. And if I just think about units, I'm very close to what I need. I have liters on the bottom, so that part's good, but I need grams on top, and I have moles on top. So really what we could do is just convert the top guy from moles to grams, and that's really where the molar mass comes into play. So this is N2, which would be 1401 times 2, right, for the molar mass of it. And if we do that, we get 28.02 grams per mole, which is the molar mass of N2. By multiplying this by the molar mass, the moles will cancel, and that will actually leave me grams per liter, which is actually what I'm looking for here. And if we did that, 1.42 grams per liter. So what I just showed you is, again, a way you could do this problem with the ideal gas law. Really, when you use this formula, that is pretty much the ideal gas law, because if you just dissect this part of it, that is P over RT, which is exactly what we just did. And then we multiplied it by the molar mass here, which is what we just did here. So a good reminder that, in case you maybe blank out on that formula, I would always kind of default and go to the ideal gas law and really just kind of treat it like a conversion problem and just try to get everybody into the right unit. So you'll usually be good in terms of that. In terms of doing density problems with gases like that, also molar mass problems with gases as well. Any questions on where I got any of those numbers, why I did any of those things? Okay. All right, so I want to try another one here that we had next, which was this one here. We have a 2.1 liter vessel, contains 4.5 grams of a gas at 1 atmosphere and 27 degrees Celsius. What is the molar mass here of this gas? And again, we're looking for the molar mass in terms of units of grams per mole, which is the typical units of molar mass. Let's take a couple minutes to see what you come up with on this one. Okay, so looking at this one, it's kind of the same approach. We are looking for the molar mass. So molar mass, again, the units of it is grams per mole. Again, you could go right into that sort of equation that we saw on the previous page, that the molar mass is the density RT over P. But again, if you can't sort of remember this formula, this also, the molar mass is sort of based on the ideal gas law. So if we kind of think about a couple of things here, in terms of molar mass, which is what we're looking for, we do have the grams part already given to us. So we are taking 4.65 grams of it. That actually would be the top part. And that means that we do need to figure out the moles part for this gas. So if we think about all the other information given to us, we have a volume that is 2.1 liters. We have a pressure that is 1 atmosphere. We also have a temperature that's 27 degrees Celsius, which we'll add 273 to. That's going to give us 300 Kelvin. And that is everything that we have. So if we have the PV equals nRT, we have a pressure, we have a volume, we have a temperature, we always have R. And look there, we only need to solve for N, which is moles, and that obviously would be the bottom part that we need here. So if we solve for N, it would be PV over RT. And if we put in our numbers here, 1 atmosphere, volume 2.1 liters, R, which is a constant, and our temperature converted to Kelvin. Again, everybody's going to cancel out except for moles in terms of the units. And we do that 1 times 2.1 divided by our gas constant and divided by 300, not 3,000, 300, gets us 0.085, it looks like. And again, this number is the bottom number that we need. So we pretty much now have everything we need. So the molar mass here would be the grams, which was given to us, divided by the moles that we just calculated. And if we do that, we will end up with 54.5. Again, here the units are not going to cancel out. So that is going to be grams per mole, which is essentially what we're looking for. So this would hopefully also, again, demonstrate to you that, if you happen not to remember this equation, again, good place to go is always to kind of default to that ideal gas law, and you can really use it to solve for things like we just did, molar mass or density. Any questions on any of that there? Okay. So the next thing we're going to kind of talk about is gas stoichiometry. And kind of the good news on sort of gas stoichiometry is it pretty much occurs the same way as a normal stoichiometry problem. The only real difference is typically when we're doing sort of gas stoichiometry is somewhere along the way we're going to kind of use the ideal gas law is usually what will happen. So somewhere there along the way we're going to use that ideal gas law. And there's really kind of two logical places where you might use it. Probably 9 times out of 10, you will use it on the back end here of the calculation. PV equals nRT, maybe solve for something like volume of a gas that's being produced. If you were to kind of use it on the front end, again, you would probably be solving for volume on the back end. You most likely would be solving for moles, and then you could kind of do a stoichiometry problem at that point. So if you happen to need to use the ideal gas law at the front end, you probably would be solving for moles, do a regular mole to mole relationship, all that good stoichiometry stuff. On the back end there, you would start with kind of like a normal stoichiometry problem, which means you need a balanced equation, you need to convert to moles, and then kind of put your moles into the ideal gas law. And again, usually solve for a volume. So let's take a look at one here. What is the volume of CO2 that's produced at 37 degrees Celsius, 1 atmosphere, and 5.6 grams of glucose is used up in this particular reaction? So if we were to do these steps, again, we would want to kind of follow the same steps that we talked about before. First one is to balance the equation. And it does look like we're in good shape here. I see some coefficients, so I'm going to assume that's balanced, so that's all good. The next thing that we want to do is really convert what they gave us into moles. And really, the only number that we had was the 5.6 grams of our glucose. All the rest of the information is about CO2. We want to know what the volume is. They give us a temperature of 37 degrees Celsius. They also give us a pressure of the gas as well. So all that kind of temperature, pressure information is really for our CO2. So to start out with here, we're going to convert those grams that they gave us into moles. So to do that, we would go to the periodic table and get the molar mass of this guy, and taking carbon at 1201 times 6 plus oxygen or hydrogen at 1.008 times 12 and oxygen 6 times 16. That is going to give us a molar mass of this guy of 180.2 grams per mole. So 180.2 grams per mole of our glucose here. Grams are going to cancel, and that will get us 0.031 moles of glucose. So the starting of this problem, pretty similar to a basic stoichiometry problem. We want to balance the equation. We want to convert to moles. The next thing we want to do is also a basic stoichiometry problem. We're not interested here in the glucose. We are interested in our CO2. And again, from the equation, we can see that for every 1 mole of glucose, we get 6 moles of CO2. So step 3 would be a stoichiometry problem here, where we're going to use that mole to mole relationship to do that. Again, we're not interested in the glucose. We are interested in the CO2. So from the equation, for every 1 mole of this guy, we get 6 moles of our CO2. And that's going to essentially get us 0.187, we'll call it. Maybe, yeah. 0.187 moles of CO2. Any questions on that so far? So, really, the first few steps here, just like a basic stoichiometry problem, the only difference is we're not interested in grams of CO2. We're not interested in moles of CO2. We're interested in the volume of CO2. And since CO2 is a gas, what we now have in addition to pressure temperature is we now have the N of CO2 as well. We always have R. So this is again where sort of a gas stoichiometry problem is different. At this point, we can use the ideal gas law for CO2. Again, we now have the pressure, we have the temperature, we have R, and we have N. So that means that V would equal nRT over P. Putting in our numbers, we get 0.187 moles. We got our gas constant there. We have our temperature, which was 37 plus 273. That's 310. Divided by our pressure, which was 1 atmosphere. Again, moles will cancel, Kelvin will cancel, atmospheres will cancel. This is going to give us our volume in liters. So 0.187 times 0.08206 times 310, going to give us 4.76 liters of, or no, 76, I said it right, read it wrong. 4.76 liters of CO2 would be produced in this case. This would be something like the theoretical yield of CO2 in volume or liters. Any questions on those steps? Again, basic stoichiometry steps here. As you can see at the end of the problem, we use the ideal gas law, which is very, very common. This was a basic stoichiometry problem. We were only given the starting amount of one reactant, so we didn't have to worry about limiting reagents or anything like that. Any questions on any of that, where any of the numbers came from? Okay. All right, so why don't you try one here? So in this particular reaction, calculate the volume of hydrogen gas that's produced at STP when we react 5 grams of magnesium with excess HCl. Magnesium from the periodic table, 2431 grams per mole. All right, take a couple minutes, see what you come up with. We're looking for the volume of hydrogen gas being produced in this reaction. Okay, so taking sort of the same approach here, definitely a stoichiometry problem. We are given the grams of magnesium here. We're ultimately looking for how much hydrogen gas we're going to sort of produce here. So we're looking for the volume of this guy here. And it is at STP. So remember, when it does say STP, it does represent a temperature. Temperature is 273 Kelvin. Pressure is 1 atmosphere at that point. Again, you always have R given to you. So if we just sort of think about our PV equals nRT, we do have obviously pressure, temperature. We are looking for the volume. We do have R, and the only thing that we would be missing here is N in terms of the hydrogen gas. So we do need a way to get to moles of the hydrogen gas, and that again is where our grams of magnesium are going to come into play in stoichiometry. The equation looks balanced, which means the next thing we want to do really is take the grams of magnesium. Using the molar mass from the periodic table there, we're going to convert it into moles. And it looks like we will get something like 0.206 moles of magnesium. Again, that's close to what we want, but we do want to get to our H2, and that's where the stoichiometry is going to come into play. So 1 mole magnesium from the equation gives us 1 mole of H2. That means that we could then convert these moles of magnesium into moles of H2, which is what we're looking for. Moles of magnesium will cancel. I could probably still do that math there, 0.206 moles of hydrogen. So now we have it in hydrogen, which is what we're looking for. We should now have everything we kind of need to go into our PV equals nRT. Here we will solve for volume, which is what we're looking for. And putting in all of our numbers in the proper spot, 0.206 moles, our 0.08206 for our gas constant, our temperature of 273, and our pressure here of 1 atmosphere. Everybody's going to cancel out except for the volume, which will be in liters. And if we do that, looks like we are going to end up with about 4.61 liters. Again, that would be how much hydrogen gas we would be expected or expect to produce in this case. Also, would be sort of the um, theoretical yield in terms of volume in this particular case. Question on that particular one there. Now, some of you maybe solved it a different way, and if you did, it would revolve around this actually being at STP. And because it is at STP, we could have used that 1 mole is 22.414 liters instead of using the ideal gas law, which means we could have just picked up the calculation from this point where we had moles of H2 and just simply use that conversion factor. That 1 mole of H2 in this case would be 22.414 liters. The moles will cancel out, and you should end up with 4.61 liters as well. So that would be an alternative approach you could do. As you can see, you do get the same answer no matter what. Um, no matter what there, whichever way you go here. And we do you can use this because it's at STP. Remember, you cannot use it if it is not at STP conditions. So the only time you could use this is at STP. And that, to answer their question, that is why was 273 the temperature. That's basically what STP means. It means the temperature is 273 Kelvin and the pressure is 1 atmosphere at STP. Any questions on how to solve those two different ways? And again, it just shows you, like most things with gases, if you can't remember a particular formula, sometimes a lot of things do fall back to sort of the ideal gas law as well. Okay, you could definitely have a sort of limiting reagent problem as well with gas stoichiometry. Again, you would approach it the same way. You have to figure out the limiting reagent if you did have something like that. So the next thing we're going to talk about is basically Dalton's law of partial pressures. And basically the idea here is when we have gases, a lot of times it is a mixture. Uh, it is a mixture to I know I'm trying to read and talk at the same time. It's really hard sometimes when you try to. Uh, Sometimes when gases do come together, it is a mixture of gases. And to answer sort of the questions I think coming through here, again, a reminder: STP is not 25 degrees Celsius. It's actually 0 degrees Celsius or 273 Kelvin, basically. And the pressure, like I said, is 1 atmosphere or 760 torr millimeters of mercury. Yeah. All right. So when we do have gases that come, a lot of times they, like I said, do come as sort of a mixture. So in this sort of example here, if we wanted the pressure or the total pressure of this, because there's really only one sort of gas molecule present, P1, I think it's called, it would be the pressure associated with pretty much P1 there. Since it's the only gas molecules that are flying around, they're the only ones that will cause collisions and raise the pressure. If we wanted the total pressure of this guy, which is just kind of the green gas molecules, our P2, it would be the pressure of P2. But if we kind of mix them together here in this last one, we do end up getting a mixture of gases, and each of them are going to contribute to the overall pressure of that mixture. So in this particular case, the total pressure would be the pressure of gas 1 plus the pressure of gas 2. And these individual sort of pressures of these gases, these are what are referred to as being partial pressures because they partially contribute to the overall pressure of that system when we have a mixture of gases. Now, how do we get to the pressure of a gas in a mixture? The most common way a lot of times is using the ideal gas law, PV equals nRT. But a couple of things about our mixture here is, as it just popped up here, because these guys are pretty much in the same container, for all the gases that are in that container, they will have the same volume and they will also have the same temperature because that container is basically sitting in the same location. So usually when we go and solve for the ideal gas law here, we would solve for P for each gas individually. And really the only thing that's usually different between the gases is the number of moles, since temperature and volume are going to be the same for all the gases that are in there. Now, as we'll talk about a little bit later on this chapter, because these are usually considered ideal gases, even though they are flying around in the container with other gas molecules, it's assumed that they pretty much have no interactions with each other. So what we could essentially assume is, even though there's multiple gases in this container, we could assume that they're kind of in there by themselves. So that makes the calculation a lot easier. And again, that's really something, as we'll talk about a little bit later here, that's something that makes something an ideal gas, is that idea that there's really no interaction between different gas molecules, even if they're sort of in the same container under sort of normal conditions. So like I said before, the really easy way to sort of calculate it is just simply to solve for the ideal gas law individually for every gas that's in there. And then when you want the total pressure, you just simply add up all the partial pressures together. So if there's two gases, you add up all the partial pressures of those guys together. Three gases, you add them all together. Now, there are certain cases where you're maybe not given enough information to actually use the ideal gas law. And when you're not given enough information to use the ideal gas law, you can sometimes use an equation that will help you figure it out if you pretty much know the number of moles of the gases that are present. So we could use this one. This is the partial pressure of a gas. X to the I is what we saw, I think, in the last chapter. That is our mole fraction. So remember, the mole fraction is the moles of the gas you're interested in divided by the total moles, which is what this is. So if we wanted the mole fraction for gas A, we would take the moles of gas A and divide it by the total moles. Remember, when you do a mole fraction, you're not multiplying by 100, so it's not like a percentage. So don't do the multiplying by 100. Same thing if we wanted the mole fraction of B. We would take the moles of B divided by the total moles. And PT at the end here is the total pressure. So this equation or formula here is really useful, again, for a situation where maybe they don't give you temperatures, maybe they don't necessarily give you volumes or anything like that, but they do give you enough information to get the moles of everybody. And maybe they give you either one partial pressure, maybe they give you the total pressure. So that's a very useful sort of formula for that. The other one, again, is just simply using the ideal gas law individually for each gas and then adding them everybody together. Any questions on that one there? Okay. All right, so why don't you try one here? 5 grams of helium added to 5 grams of neon in a 2.5 liter container at 27 degrees Celsius. Calculate the partial pressures of each gas and also calculate the total pressure. So helium is 4.003 grams per mole. Neon is 2018 grams per mole. All right, take a couple minutes, see what you come up with. Should have 3 answers, 2 partial pressures, and a total pressure. Okay, so we are looking for really two partial pressures. We're also looking for the total pressure when we kind of add it all together. So we basically have a container that contains both of those gases flying around. So again, even though they're sort of in the same container, we're going to assume that they're really not interacting with each other. Again, that's really something that makes something an ideal gas. So we do have some information. We do have obviously the volume, which is 2.5 liters. We have a temperature that's 27 plus a 273, going to be 300 Kelvin. And we want to calculate the pressure, obviously, in this case, of each gas. So we are going to use our PV equals nRT. And we're really going to solve for P for each of the gases, again, individually. But we do need to figure out the moles of each gas. So using the periodic table there and our starting ones, we get the moles of helium would be our 5 grams divided by our 4.003 grams per mole. Going to give us something like 1.25 moles of helium. We could also do the exact same thing here for our neon. We're going to take our 5 grams of neon. We're going to divide it by its molar mass of 20.18. Grams are going to cancel, going to give us 0.248 moles of neon. So at this point, we now really have everything we need for both gases. So if we start with our, some stuff out of my way here. If we start for the partial pressure here of helium, again, it's going to be nRT over V, and we're going to use the moles of our helium, which is 1.25. We're going to use R, which is our 0.08206. We're going to use our temperature, which is 300 Kelvin here, all divided by our volume, which is 2.5 liters. In terms of units, everybody's going to cancel out except for atmospheres. And if we do that, we end up with something like 12.3 atmospheres for helium. That is what is referred to as the partial pressure of helium. Now, for neon, we're essentially going to do the identical calculation. The only difference is we're going to use the moles of neon in this case, and that would be 0.248 times our R times our temperature and divided by our volume. Again, the same units are going to cancel out, going to leave us just atmospheres. And it looks like perhaps we have 2.44 atmospheres. And that would be our partial pressure of neon. Any questions on those two numbers? Now that we have the partial pressures, to find the total pressure, we're just going to add them together. So it would be the partial pressure of helium plus the partial pressure of neon, giving us 12.3 plus 2.44, and going to end up with 14.7 atmospheres in this particular case. And that would be our total pressure. Any questions on any of the steps there, where we got anything from? We could also see that in this mixture of gases, it is actually the helium that's actually the major contributor to the pressure. And we'll actually talk about why that is in this chapter, but a preview would be it's this reason right here. Helium is only 4 grams per mole, while neon is 20 grams per mole. So neon is heavier, which means it's going to be flying around slower than our helium, which is moving around a lot faster because it's lighter. And because helium is moving around faster, it's going to cause more collisions and be responsible for more of the pressure in that mixture. Any questions on that? Let's try the next one here. We have a natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. What is the total? If the total pressure is 1.37, we're looking for the partial pressure of propane, the C3H8. So see what you come up with. Okay, so in this particular case, we are given the moles of this mixture of gas here, and we are given the total pressure, and that's pretty much it. We're not given any type of temperatures, we have no volumes, nothing like that. But we do have the moles of everybody, so that does allow us to use that other partial pressure formula that we saw earlier, which is this one again. Partial pressure of a gas is the mole fraction of that guy times the total pressure in this particular case. So the first thing we want to figure out is the mole fraction of what we're interested in, which in this case is the propane, the C3H8. In order to do that, that is the moles of propane divided by the total moles in this case. So we could just simply add up all of our moles here. So we have 8.24 plus 0.421 plus 0.116 moles. And this will give us our total moles in this case, which looks like it is 8.777. So to find the mole fraction again of our propane, we're going to take the moles of propane, which in this case was 0.116, I believe, 0.116, divided by our total moles, which is 8.77 moles. Remember here, it is not a percentage, so we're not going to multiply by 100 or anything like that. And we're going to divide, and it gets just something like 0.0132 as our mole fraction in this particular case. And we then can use that here, and we have the total pressure given to us. So to find the partial pressure of this guy, it would be its mole fraction times the total pressure. So that's going to give us 0.0132 times our 1.37 atmospheres. And we will end up with, looks like 0.0181 atmospheres as the partial pressure of propane in this particular case. We obviously could do it for the other gases if we wanted to. We would just find the mole fraction of each of the other ones and then basically times it by 1.37, and that will give us our partial pressures of each of those gases. Any questions on that particular one there? So these are two types of partial pressure problems. One is sort of a common type where you use the ideal gas law. The other one, like this, where you have everybody in moles. Maybe you don't have everybody in moles, but you have everybody in grams, and you can't get from grams to moles. So again, it doesn't necessarily have to be in moles given to you, but it does have to be in some unit that you're able to get to moles of everybody, and then you can use this equation. Any questions on those two there? Now, another partial pressure situation does develop a lot of times based on how gases are collected. And a very common way gases are collected is a setup, for example, like what we see here in this picture. But the basic setup is we fill some type of container with water, and we basically put a tube into that container, and we run the reaction. And basically, as the reaction goes, the gas goes through the tube, goes into the container, and basically displaces the water that's in there and replaces it with the gas we're interested in. So if we look at this particular reaction here, which is potassium chlorate, if we heat it up, it will do a decomposition reaction and it will produce some oxygen gas. And as we are heating it here, the oxygen gas is being generated. The oxygen gas is going through the tube into our container and starting to bubble up. And what's happening is the water will come out, the gas will go in, and eventually, when the reaction's over, we'll have this sort of empty space in this container. And it's really not empty. It actually has the gas we're interested in. So in this particular case, it would be oxygen gas. It would be collecting in sort of that empty spot of that beaker or whatever it may be. But a consequence of sort of doing this reaction here in the presence of water is when we do a reaction, oftentimes there's heat involved. And when we get heat with water, we usually will get water to evaporate. And when water evaporates in this empty spot here where we have our oxygen gas, which is what we're interested in, we also get some water vapor that basically enters into that empty space. So now what we end up with is a mixture of gases, which we're not really interested in the water part, but it is a mixture, and it's basically the total pressure in this type of situation would be the partial pressure of the gas you're interested in plus the pressure of water at a given temperature. And this is what is referred to as the vapor pressure of water. And that is typically a value that you could go and look up in a table. So that's a value you could go and look up in a table. It is based off of temperature. So usually when we have this type of situation, we need to do sort of a correction calculation. And we could rearrange that top equation and find that the pressure of the gas is equal to the total pressure, which in a laboratory would be the barometer reading, minus the vapor pressure of water, which would come from a table in that particular case. And this will give us the partial pressure of the gas we're actually interested in. In this example here, it would be oxygen. It is sometimes referred to as getting the pressure of the dry gas because we're kind of subtracting water's contribution to it away and sort of taking away water. So sometimes referred to as the dry gas pressure in that particular case. Now, how do you know you have this situation? Usually there's some keys in terms of sort of the problem. It will say something like you collected the gas over water, you collected the gas saturated with water vapor. It will mention something to do with water, basically. And that's how you know typically you need to kind of go and do that little correction value to get rid of water's contribution. Because again, you're usually not interested at all in the water. So in this particular example, we wouldn't be interested in the water here. We would be interested in just the oxygen gas because that's the gas we're actually collecting as a result of the reaction that is taking place. And here is a table of the vapor pressure of water at different temperatures. And again, it's just simply a value that you just look up and you can use it. So if we try one here, a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr, and the vapor pressure of water at 30 degrees Celsius is 31.824 torr. What is the partial pressure of oxygen? So the key words here is saturated with water vapor. That tells you that you have that situation we just talked about. We have the total pressure is the pressure of the gas we're interested in, plus the vapor pressure of water at that particular point. In this case, we are looking for oxygen gas, and we looked up the value here at 30 degrees Celsius. That value would come from a table such as this. So value would come from a table such as the one we see here. And we basically have everything we need. We have the total pressure, we have the vapor pressure of water. So in this case, we can solve for the pressure of oxygen gas. So the partial pressure of oxygen would be our total pressure minus the vapor pressure of water at that temperature. Our total pressure being 753 torr minus our 31.824, which is our vapor pressure of water at 30 degrees Celsius. And again, we would get this value from a table. And if we do that, we end up with something like 721 torr, we will call it. We do want it in atmospheres, so we would divide this by 760. And that would get us something like 0.949 atmospheres of O2. And again, that would represent the pressure of, sometimes referred to, the dry gas, because we sort of got rid of water's contribution. Any questions on any of those steps there? Okay, so there's a few different types of partial pressure problems we talked about. Again, one where you kind of use the ideal gas law, one you don't have enough information for the ideal gas law, so you use the mole fraction. And lastly here, a very common one, where you collect the gas over water or saturated with water vapor. So you do have to do sort of a correction value to get yourself to the pressure of the gas you're actually interested in. Any questions on that there? So that does bring us to the kinetic molecular theory of gases, and these are some important sort of information about gases, some of which we sort of touched upon, but let's talk about these guys here. A gas is really composed of, are separated by molecules that are distances are greater than their own dimensions. So they're thought of as being sort of points, and they don't really possess a mass. They do possess a mass, but they really don't possess a volume. So under normal sort of conditions, the volume of the gas itself is basically relatively small in comparison to the volume of the container it's in. So we think of the volume as being negligible or zero in that particular case. Gas molecules are in constant motion, random directions. They frequently collide with one another. We assume these collisions are perfectly elastic, so nobody's slowing down or anything like that. They just basically bounce off and move around. Gas molecules exert neither attractive or repulsive type forces on one another. And lastly, the average kinetic energy of a molecule is proportional to the temperature. So basically, as we increase the temperature, we would expect the gas molecules to gain more energy, to fly around faster, and thus probably create more collisions and pressure, and vice versa if we lower the temperature down. So there are really two things here that make something an ideal gas. And it's these two things that I circled and boxed. These two things here, where we assume that under normal conditions of pressure and temperature, the gas itself has no volume, it's negligible compared to the volume of the container. And secondly, there are no attractive forces or repulsive forces between gas molecules that are in the same container. And that is what makes something an ideal gas, these two things really. That is also why we were just able to, in a situation where we had, for example, helium and neon in the same container, we could essentially assume that they were in there by themselves and they weren't really interacting with one another. And that's because we assume this sort of ideal behavior. Why is it important that there's no attractive forces between one gas molecule and another? So the idea here is if we have a gas molecule that's ideal, it pretty much, for example, has a clear path to hit the wall of the container. And that would be different if that gas molecule, which is shooting towards the container's wall, actually felt some attraction to another gas container. What it would kind of do is like put the brakes on it. So it would take maybe longer for it to hit the wall, maybe won't hit the wall as hard as it normally would if there was some attractive forces. Also, as well, if there was repulsive forces, if these two guys repulsed each other, this gas molecule that was heading towards the wall may actually move away a lot quicker and hit the wall a lot quicker and also create a lot more difference in terms of the pressure. So we sort of assume these sort of ideal situations here, which again is what makes something an ideal gas, is really those 2 points of it. And that's why we can, what we did, not really have to worry about the other gases when we're doing something like partial pressures. Any questions on that there? Okay, so some of these reminders of the things that we talked about along the way here with our gas laws. Again, with Boyle's law, we saw that inverse relationship. As one went up, the other went down. So as the volume went up, the pressure went down, and vice versa. With our Charles law, we did see that as the volume went up, so did the temperature. Volume goes down, so does the temperature. That again is the way it's able to maintain constant pressure. With Guy-Lussac's law, we saw that if the volume does not move and we increase the temperature, we would expect the pressure to increase, and vice versa. If we lower the temperature, we would expect the pressure to decrease as well. Avogadro's law, we saw really that the collision rates are proportional to the number of gas molecules. And that again is the one where we saw we could kind of do some stoichiometry at constant temperature and pressure, that we could do sort of a volume to volume relationship, just like we do a multiple relationship in stoichiometry when we're in those sort of conditions. And lastly, as we see here, and we just talked about, there's no attractive forces or repulsive type forces between the gas molecules. Thus, we can assume that they're in there by themselves, and we could do our sort of partial pressures as one is unaffected by the presence of another gas. Any questions on the kinetic molecular theory there of gases? All right, we will lay it up here for lecture for today. So we do have a quiz today. We also are doing the next part of the experiment. So what I've decided is we will meet at 7:15. We'll talk about part two's calculations, which shouldn't take very long. And then for maybe around 8ish, the quiz will open. You can take the quiz at that point. So that way we could cover part two of the experiment, still stay on pace, and I'll post part twos